In the last video, number 1 in this series, we thought about some of the ways in which Newton's theory of gravitation seemed to give some confusing inconsistencies or slight problems in interpretation. Namely, there seem to be two types of mass, inertial mass and gravitational mass, or at least mass has two very distinct properties, one to do with the difficulty of changing its motion, and one to do with how it attracts other masses, and yet we treat it as the same thing, mass. Secondly, gravitational fields are never really uniform fields. They're always converging near large masses and maybe diverging in parts of complex systems, but they're never truly uniform over extended space. Thirdly, the definitions of weight and weightless in Newtonian gravitation seem somewhat confusing, both in the definition of weight and in the language used, for example, when we talk about weightlessness. And we want now to add a fourth thing to this list, and it relates to what we call non-inertial frames of reference. First, however, we'll have a short discussion and say a little bit about inertial frames of reference. In all of this, we'll take the idea of a frame of reference to mean a kind of spatial coordinate measuring system, which has numbers attached to it, and which allows us to locate things in a particular space, or if you like, at the simplest level, to find the position of things in that frame. For example, in the two-dimensional space of this flat screen, the typical thing would be to use a simple set of Cartesian coordinates, x and y, like this. It's shown here with the coordinate lines drawn in red, and a black edge has been put around the frame. This outer edge is only for convenience. You should, of course, think of these x and y scales as going on forever in both the positive and negative directions beyond the screen. This is a frame of reference for the whole of this two-dimensional space. Notice that I haven't put numbers or scales on the axes, but simply want to show the grid of the coordinate system. I will also now, rather than using x and y, use x1 and x2 for the two sets of coordinates, and I'll put the 1 and 2 as upper indices, like this. I won't explain why at this stage we're using upper indices or superscripts rather than anything more obvious. If you've never come across this before, it may seem a bit bizarre, but we're going to do it in order to try to get a little used to what we will be forced to use later on, if we go on to think about general relativity. So bear with me. When eventually we have to deal with the 4 dimensions of space-time, we will use for our 4 coordinates x0, x1, x2 and x3 with upper indices or superscripts 0, 1, 2 and 3. These will represent time, the x direction, the y direction and the z direction. This will be an important way of designating the 4 dimensions, and so we might as well spend a little time here getting used to it. X and Y will, for most of the next few videos in this series, always be designated as x1 and x2. You should also fix in your mind that these are indices and not exponents or powers. This is not x squared, it's x2 or y. And if we ever need to write x2 squared, which is really y squared, we will have to put it in a bracket like this. Now granted, this looks awful, but fortunately things like this will hardly ever be needed, and the benefits of using upper indices for x1, x2, x3, which may seem rather strange at this stage, should become clearer later. So, this Cartesian red grid of x1 and x2 is a useful frame of reference, which will enable us to measure where things are in the two-dimensional space of this screen. We simply take the 2 orthogonal measurements x1 and x2, or if you like x and y, and we know exactly where something is. Of course, somebody else making measurements in the same space of the screen could be using an entirely different set of coordinates to this red frame of reference. Let's assume that their coordinate system is only very slightly different, being the same kind of Cartesian coordinates, but perhaps shifted over slightly, and maybe with a different sizing between the grid values. Now granted, this doesn't look much different here, but just assume that it's displaced in some way and maybe the scale is shrunk or it's in centimetres instead of metres or whatever. We've shown this frame of reference in blue. And of course, once again, the box around it is only for the convenience of drawing. You should think of these coordinates axes as going on forever in each direction. Also, these blue axes have been labelled x1 and x2 with a tilde on top of each, simply to distinguish any measurements of position made using this blue coordinate system from those made using the original red set of coordinates x1 and x2. If we wish to describe the position of a point on the screen, we could either use x1 and x2 values from the red frame or x1 tilde and x2 tilde values from the blue frame, and we could of course relate one to the other providing we know the relative positions and scale differences of the two sets of axes or frames of reference. In other words, we can easily convert the blue x1 tilde and x2 tilde values to the red x1 and x2 values, and vice versa, as long as we have all the information about how the two frames are related to one another. It should also be obvious that if we imagine some physics experiment taking place in this space, in the space of the screen, then it wouldn't really matter which set of coordinates we use to make measurements during the experiment. The physics would be the same whether we use the red x1 and x2 or the blue x1 tilde and x2 tilde, and any conclusions from the experiments should be identical. We're imagining Earth-like conditions but in two dimensions, so that we could imagine some kind of very simple physics experiment being done, but in two dimensions. For illustration, we'll consider an experiment like the simple pendulum taking place within a particular plane. And we'll make that plane the plane of the screen, and we'll ignore the third dimension in and out of the screen. So let's imagine two people standing at the origin of each frame of reference, the red and the blue, each doing exactly the same experiment. When at rest, the pendulum of each of the observers would hang vertically downwards under the force of gravity on the mass of the pendulum. If each pendulum was disturbed slightly, then they would each oscillate back and forth. Let's therefore assume that the two people then performed the traditional simple pendulum experiment that's often done in schools. They would each alter the length of their pendulum, set it oscillating, and measure the time period for different lengths, and then plot some kind of graph. If you remember your high school physics, the approximate time period t of a simple pendulum on the Earth is given by 2 pi root L over g, where L is the length of the pendulum and g is the acceleration due to gravity or gravitational field strength at the surface of the Earth. And it's usual in such an experiment to take the length L and time t measurements and then plot a graph such as t squared against L. And if both experimenters did this, then the results of the two experiments, using different coordinates and in different places, would be identical, as long as we made the conversion for any difference in the scales of the two frames of reference. Each experiment would give a straight line passing through the origin, and they would each get the same value of g from the calculation based on the gradient, after conversion of units, of course. Now all that should be pretty obvious. So let's now think about what happens when one of the people and their frame of reference is moving. Let's imagine that the person using the blue frame of reference is moving at a constant velocity with respect to the red axis, and let's assume that the same experiment is done as before by each of the two people. To give a context, we'll imagine the person using the red frame of reference doing their pendulum experiment on a railway station platform. They are in what we might call the rest frame. The pendulum is initially undisturbed and would hang vertically downwards. They would then set the pendulum oscillating, measure the length and time period, and then repeat the measurements for different lengths of the string. And after doing this and plotting the graph, they will obtain the result that we've just described. The other person and their blue frame of reference we'll place on a train. It will leave the station, leave the red person behind, pick up speed, and we will assume that eventually it will travel at a constant velocity relative to the red person left behind on the platform. So we now have the blue person using the blue frame of reference travelling at a constant velocity relative to the red system. And I'm sure you realise that once again, providing the motion of the train is perfectly smooth, the person doing the experiment in the train would start off by seeing their undisturbed pendulum hanging vertically downwards, exactly as before, even though the train is moving. When this pendulum is disturbed from its equilibrium situation by giving it a knock, it would oscillate around the vertical in exactly the same way as that of the person on the platform who was using the red coordinates. The fact that the train and the pendulum of the blue frame of reference are travelling at a constant velocity relative to the red frame will have no effect on the result of their experiment. Each of the two observers, red and blue, will reach the same conclusions as one another and obtain exactly the same calculated value of the acceleration due to gravity g with an experimental error and having made any adjustment for their different scales. These two frames of reference travelling at constant velocity relative to one another are known as inertial frames. And from our discussion about inertial mass, you can possibly see where the word inertial comes from. It comes from the fact that even though the train is moving, there are no extra forces on the masses in the blue frame in the train carriage that could make the result of any experiment different from that in the red, or what we're calling the rest frame. Einstein's special theory of relativity dealt with these kinds of constant velocity frames of reference, these inertial frames, and it did so at both low and high velocities. Now granted, there were some radical consequences which followed from the idea that the velocity of light was the same in all inertial frames, but it did only apply to inertial frames. It did not deal with frames of reference which are accelerating relative to one another, and you can easily see why. The forces producing any accelerations would in all likelihood mess things up. So let's think about that a little. Still ignoring special relativity and keeping to relatively low velocities, let's go back to the train experiments. And let's imagine a third situation where the train and the person in it using the blue coordinate system are accelerating uniformly relative to the outside observer back on the platform, the one using the red frame of reference. We'll assume that the train keeps on accelerating with the same acceleration for a long period of time, and the velocity never gets ridiculously high, even though that idea would be somewhat impractical for a decent-sized acceleration and for the time needed to do a reasonable experiment. Note that in order to stand up vertically, the person would probably either have to lean forward or, as shown here, hold on to something to stop falling. This time, with the train accelerating, even when the pendulum in the carriage was undisturbed and at equilibrium, it would not hang down vertically in the train. We could think in terms of the top of the string being pulled with a constant force to the right because of its connection to the accelerating train via the person holding it, or maybe some mechanical support if it had one. The string in turn would pull to the right and keep on pulling the mass at the other end of the pendulum in order to increase its speed to the right faster and faster, so it keeps up with the accelerating train. The pendulum would come to equilibrium at some angle to what would be the vertical of the carriage, even though the train was travelling on a level track. The forces on the pendulum in this accelerating train would clearly not be the same as those experienced by the person back on the platform in the red rest frame. If we then set the pendulum on the train oscillating, then the movement of the pendulum would also be different to that of the experiment done on the station platform, the red coordinates. The pendulum would oscillate about its new central position, the dashed line shown here. More than that, however, we would reach a different conclusion for the experiment. We would get a different answer, even after converting between the units of the two systems. we would get a smaller gradient of the graph for this experiment and hence a larger value for the apparent acceleration due to gravity, and we'll discuss all that in a moment. In this situation, where the blue frame is accelerating with respect to the red frame, we say that we are dealing with two non-inertial frames of reference. Granted, for this simple example of a train and a pendulum, we know enough basic Newtonian physics to be able to make corrections for the acceleration of the train, and then see that the physics deep down is actually the same. But the straightforward equations wouldn't say so. On account of the extra forces involved, we would, on the face of it, get different answers for the gradient of the graph, even after any conversion for differences in the scales of the two reference frames. Part of making sense of this from straightforward Newtonian physics could be to think in terms of the force of gravity on the pendulum having something added to it, and so the effective acceleration of gravity has a different size and direction. What I mean is, with the train accelerating to the right with acceleration a, it appears that the Earth's gravitational field g, which acts downwards on the pendulum, seems to have an extra horizontal force field added to it, which is in the opposite direction to the acceleration of the train. And I could write this as minus a and add it to g using this vector diagram. The pendulum can be thought to be experiencing both of these accelerations, g and minus a. They can both be thought to be acting on the pendulum. You may notice here that the g and a are now being written in bold, and I'm going to try from now on to show all vectors with their symbols in bold in order to distinguish them, even though some equations may not be rigorously written as vector equations. Anyway, this minus a seems a bit like an extra gravitational field, because the consequence of adding these two vectors g and a is that inside the accelerating train there seems to be what you might call a new vertical in the direction of g dashed, and the oscillation of the pendulum would take place around this new vertical direction. Clearly the new g dashed is bigger than the old g, and so the result of the experiment in the blue accelerating frame will be different to that in the red rest frame. It will give a bigger value of g or g dashed, the acceleration due to gravity. The physics seems, at least on the face of it, to have changed. Now you may try to argue against this conclusion by suggesting that the Newtonian solution that we've just given is so obvious because you can see the surroundings, you can see the view outside the window of the train. You might say that you would know that you were accelerating, and you could modify the Newtonian equations, make correction, and eventually see that the two answers for the real acceleration due to gravity were actually the same. The physics hasn't really changed at all, and in a way, of course, you will be right. However, suppose you could not see the outside world, because there were no windows in the train. Imagine that the windows here were completely covered. You might well interpret what was happening by assuming that the train was climbing a hill and was travelling at a constant velocity up the hill. In exactly the same way as before, you would either have to lean forward to get in line with the new g dash, the new vertical, or as here, hold on to one of the seats to be perpendicular to the floor of the train. As far as you would know, you would be travelling at constant velocity uphill, and the new g dashed would be the acceleration due to gravity of the Earth. The fact that you have to lean forward or hold on would be interpreted as being because you're going up a hill. In other words, with no windows in the carriage, you would not be able to tell whether you were accelerating on the flat, and the value of g has not changed, or you were going up a hill at a constant velocity, and the value of g has changed. If, of course, you did assume you were travelling with constant velocity up a hill, then you could also suggest that you were the one at rest, any inertial frame can assume that it is the one at rest. Being on a hill at rest would make the pendulum hang in exactly this way, such that its angle to the floor was not perpendicular. All of that would be a legitimate interpretation in this smoothly accelerating train carriage with no windows. However, the value of the acceleration due to gravity measured by your experiment would be g' bigger than g, and in this way the accelerating blue frame of reference would, in a sense, have changed the physics with respect to that in the red frame of reference, the rest frame. And this is what Einstein reacted against. He didn't like it. It seemed reasonable to him to say that even though you can't see what's going on, the laws of physics must be the same. They must be the same not only in inertial frames, but in accelerating frames of reference as well. And he suggested that there must be a way of writing down the laws of physics so that all of this is taken into account, even without being able to see outside and make corrections. Such a solution would also, of course, eventually have to bring in the idea of high velocities and the velocity of light, again without having the physics change, but that's not part of our discussion just yet. The starting point for us in this new way of thinking is the idea that we have been hinting at, that a uniform acceleration seems to mimic the existence of an extra gravitational field, and this idea is known as the Equivalence Principle, and it's worth spending some time discussing it further. From our consideration in the last video about Newtonian mechanics and gravitation, and from what we've just been thinking about, a number of questions have arisen. Firstly, there seem to be two types of mass, inertial mass and gravitational mass, or at least mass has two very distinct properties, one to do with the difficulty of changing its motion, and one to do with how it attracts other masses. Secondly, gravitational fields can never really be uniform fields. Thirdly, the definitions of weight and weightlessness seem confusing, both in the definition of weight as the force of gravity on an object, and in the language used, for example, when we talk about weightlessness. Fourthly, the laws of physics seem to change in an accelerating frame of reference. An acceleration seems to mimic an extra force of gravity, albeit what seems like a uniform gravitational field. Having earlier developed his special theory of relativity in 1905 and shown that the laws of physics are the same in all inertial frames, even with the complication of high velocities and the constancy of the speed of light in all such frames, Einstein was keen to be able to show that the laws of physics must be capable of being written in such a way that they are also the same in non-inertial frames of reference. In other words, when one of the reference frames was undergoing some sort of acceleration. He wanted to deal with number 4 here, so that acceleration was included automatically in the theory. This would mean, of course, that because acceleration seemed to mimic gravity, then gravity would automatically be included in the theory as well. And in developing what became known as his general theory of relativity, he also took away something of the mystery of the first 3 questions. So, once again, our starting point in exploring all of this will be to ignore high velocities for the time being. Any movement will be at speeds much less than the speed of light, even if we have an acceleration which goes on for a long time. Also, we will make a very simple assertion, namely what is called the Equivalence Principle. And this can be loosely stated in many different ways, and I'll start by giving this rather imprecise version of it, namely that in some ways gravity is the same as an acceleration. Now, I'm sure you realise the vagueness of this statement, starting as it does with "in some ways," but you'll also realise that the second part of this statement is what seems to follow from the discussion we've just had about Newtonian gravitation and about accelerating frames of reference. The simplistic argument for the equivalence principle goes something like this. Imagine a person is in some sort of closed box which has no windows, and they can't see what's going on outside. They could be in a simple kind of spaceship. Let's also assume for the moment that this spaceship is infinitely far away from any star or planet or other large mass, so that the gravitational field in the region of the spaceship is zero, apart from what it produces itself, of course. Clearly, according to Newtonian gravity, there will be no forces on the person inside the spaceship or on the spaceship itself from any other objects, and hence there will be no Newtonian acceleration of either. The person would float around in the spaceship and would be truly weightless in the Newtonian sense. The Newtonian force of gravity on them would be zero. However, if the rocket ship switched on its engines so that it was accelerating, let's say with a value of g, the same value of acceleration that we experience on Earth, the person in the spaceship would be pinned to the floor. This is because as the spaceship accelerates, the floor would hit the person's feet and keep on pushing on their feet in order that they also would accelerate in the same way as the spaceship, continuously. In order to keep accelerating like this, there would have to be a continued force upwards on the person's feet. And the effect of this is that the person would feel as though they were being pressed to the floor by some kind of force, a bit like their weight on Earth, even though the only force involved here is the contact force upwards on their feet. Now compare this situation with the same spaceship being stationary and resting on Earth. According to Newton, the person in the spaceship resting on the Earth would have the force of gravity acting vertically down on them, pinning them to the floor. Assuming this force of gravity could be perfectly uniform, they would not actually feel it. It would, in the Newtonian sense, act on every molecule of their body in the same direction and produce the same acceleration, and there would be no sensation felt from any nerves of their body. However, what they will feel is the normal reaction of the floor pushing up on their feet, and it is this that will give them the sensation of their weight. Now, the equivalence principle says that these two situations, an isolated rocket which has a constant acceleration g, and a rocket resting in a uniform gravitational field on the surface of the Earth, these two situations are indistinguishable from one another. You cannot tell them apart. We'll state that vague equivalence principle again. In some ways, gravity is the same as acceleration. And I suppose another way of saying this for the situation that we've just imagined is that feeling the normal reaction from the floor that keeps us at rest in the uniform gravitational field g on the Earth's surface is the same as feeling the contact force that would give that same acceleration g when out in free space. The equivalence principle, stated more scientifically than this of course, is the start of our thinking about general relativity, and it was an important start for Einstein. When he realized it, he called it his happiest thought. In fact, he was proven to be right about it in 1919 in connection with one of the easier to understand, I think, conclusions which follow from the equivalence principle. He suggested that the equivalence principle implies that gravity can affect light. Let me explain that idea in a rather roundabout way. On the assumption that the equivalence principle was correct, Einstein concluded that gravity can bend a beam of light. Now, at first sight, that might seem ridiculous. Everyone knows that light travels in straight lines. And in any case, why should gravity affect photons of light? Photons have no mass. So what's gravity got to do with them? However, Einstein took the equivalence principle, believed it, and worked through its consequences. To put it simply, we can say that he used a simple thought experiment to apply the equivalence principle to non-inertial frames. In other words, where one of the frames of reference is undergoing an acceleration. And from that thought experiment, he concluded that gravity can bend light. How did he do that? Well, before we get to thinking about accelerations, it might be as well to clarify something of the physics of constant velocity situations and inertial frames. Imagine we have an observer in a spaceship out in free space, infinitely far away from any other large masses, away from major gravitational influences, etc. Assume there are essentially no forces of gravity on the spaceship. Consider first the simple situation of the spaceship and the observer inside, and let's call this the blue frame of reference. Assume also that there is another observer in another spaceship, the red frame of reference, and suppose there is a velocity difference of v between the two of them. We obviously can't say which one is moving. They can each justifiably say that they are the ones at rest and that the other spaceship is the moving one. Having a constant velocity difference between them, these are two inertial frames, and so, as Einstein showed with his special theory of relativity, the laws of physics are the same in each frame, providing we use the rules of special relativity where necessary. Both occupants will be floating in their spaceship, but they will be travelling at some constant velocity relative to one another. We can either think that the red frame is at rest and the blue frame is moving upwards like this, or that the blue frame is at rest and the red frame is moving downwards like this. There will be no bending of light when the velocities relative to one another are constant like this. The laws of physics say that light travels in straight lines, and let me try to illustrate that so as to avoid any confusion later when we get to thinking about acceleration. Let's take firstly the blue frame to be at rest and the red frame to be moving downwards. Suppose also that there is a laser on the inside wall of the blue spaceship and it sends a beam of light straight across from one wall to the other, parallel to the floor. It should be obvious that the observer in the blue spaceship will see the beam go straight across and parallel to the floor. The blue person assumes that they're at rest, so why wouldn't light travel in a straight line as they shone it across from wall to wall? It will leave the laser this far from the top of the spaceship and hit the opposite wall this far from the top, exactly the same. There will be no question as far as the observer inside the blue spaceship is concerned of the spaceship having moved upwards while the beam travelled across from one wall to the other. As far as the blue observer is concerned, he is the one at rest, and it's the outside red observer who seems to be moving in the downward direction. In other words, as the blue observer floats around, he sees the light beam go straight across, as is shown here. Now what about the red observer? What the person in the red spaceship and the red frame of reference sees is another matter. He actually does see the beam get deflected, and it seems to go in a straight line at an angle to the floor. Now you may need to go into special relativity to be convinced of the mathematics of this, but let's think descriptively. As far as the red observer is concerned, he is the one at rest, and it's the blue spaceship that's moving upwards at velocity v. The red observer detects the light leaving the laser this far from the top of the blue spaceship, but by the time it gets to the other wall, he detects that the blue spaceship has moved up slightly. Let's assume it's moved to this dashed position by that time. Now the red observer must agree with the blue observer as to where the laser light hits the opposite wall of the blue spaceship. So it must hit the wall at the same distance from the top of the spaceship, namely here. So, to the red observer, and from the measurements made with the red frame of reference, the light has certainly travelled in a straight line, but it has travelled upwards. Now you may at first think that the physics has changed, but it hasn't. You may think that this diagonal light path is longer than going straight across, and so the red observer measures light to have travelled faster than the speed of light, if that makes sense. Of course, that would be true for Newtonian mechanics, but in some ways that's the whole point of special relativity. The equations of special relativity, the new mechanics, take all of that into account and not only tell us that light still travels in straight lines in all inertial frames, but also that the apparently different distances and different times that people measure are all consistent with the mathematics, the new mechanics. Special relativity explains it all for inertial frames. Physics is intact. The point I want to emphasize here, though, is that the blue observer, who thinks he's the one at rest, doesn't see anything other than the beam of light going straight and parallel to the floor, even though other people could say that the blue spaceship is moving up at constant velocity and that light is being deflected. Special relativity has shown that the laws of physics hold in all inertial frames, and these are inertial frames. You shine a beam of light, and it goes in the direction in which you shone it. If you're not accelerating, then you can take yourself to be in the rest frame and assume everyone else is moving. Your world is the normal one, as far as you're concerned. So, having laboured that a bit and gotten it out of the way, what about if the blue spaceship is accelerating relative to the outside observer? And this is the crunch for general relativity and for the bending of light. For an accelerating spaceship, we don't have an inertial frame, and special relativity can't be used, at least in a straightforward way, to explain things. And, as we'll see in a moment, the person inside the accelerating spaceship will not only be pinned to the floor by the acceleration, as though they were in a uniform gravitational field, but also the acceleration will appear to bend the beam of light, at least as far as the accelerating person is concerned. Let's try and illustrate that. Consider again the laser light crossing the blue spaceship, which is now accelerating away from the non-accelerating red observer. Consider the moment that a photon leaves the laser on its side wall. The spaceship is probably already moving at some velocity at that time relative to the red observer, and if the spaceship stayed at that velocity, the person within the spaceship would perceive that the beam of photons would go straight across the spaceship, and that's what we've just been thinking about, a constant velocity situation. However, things are not quite like that. After a photon leaves the laser, the velocity of the blue spaceship increases, so that by the time the photon reaches the far wall, the spaceship has moved upwards to this dashed position. It has not simply moved upwards relative to the red observer, it has moved upwards relative to where it considered itself to be initially. When therefore the light beam arrives at the far wall, here, the blue spaceship will be in the dashed position. And that means that, as far as the blue observer is concerned, the light left the laser from this point on the left wall and arrived at this point on the right wall. Taking the starting position of the blue spaceship away from this diagram for clarity, it should be obvious that to the blue observer, to the one who is actually accelerating, the light seems to have been deflected downwards. Think about this. Even though the laser is moving with the spaceship and is in its reference frame, and even though it is sending the beam to the other wall in the direction parallel to the floor, there will, in this situation, be a deflection as perceived by the blue observer themselves, and it's all because of the acceleration of the spaceship. However, it won't be a simple linear deflection. It's not a straight line. The fact that the velocity is continuously increasing when something accelerates means that the rate of the deflection increases, and we end up with a curved path for the light as perceived by the person inside the accelerating spaceship. Now you might ask the question, what would the outside observer see, the one using the red rest frame of reference? Well, let's say for simplicity that they were travelling at the same velocity as the blue spaceship at the very start. They were both together. In other words, there's no relative velocity, and then the blue spaceship began accelerating. The red observer would always consider themselves to be at rest, and to them it would be the blue spaceship that accelerated away from them. Having the same starting velocity as the blue spaceship when the beam of light left the laser, the red observer would say that the light travelled exactly as you would expect, straight across, in a straight line, parallel to where the floor of the blue spaceship had originally been. However, they would insist that the blue spaceship accelerated upwards so that the beam then hit the other wall at a different place. So what's the point of all this? Well, the equivalence principle states that a uniform or constant acceleration can be replaced by a uniform gravitational field, one with supposedly parallel field lines. So if, instead of having the blue accelerating spaceship out in deep space with no gravity, we had the same spaceship at rest on the Earth in a more or less uniform gravitational field, we could expect the beam of light to bend in this kind of way. And this leads to the conclusion that, if the equivalence principle is true, then gravity bends light. And it was in 1919, 4 years or so after Einstein's general theory of relativity was published, that two independent teams of physicists working in Brazil and Africa showed during a total eclipse of the sun that distant starlight was bent by the sun's gravity. They measured, as best they could, the positions of background stars in the Hyades cluster close to the sun's edge during the eclipse, and then later compared their measurements with the normal positions of the same stars in the sky. The positions of the stars were altered in exactly the way that Einstein's theory had predicted, with an experimental error, and this gave an early confirmation of, at least one aspect of, the general theory of relativity. So that somewhat long digression was simply to illustrate that the equivalence principle is more than just a theoretical idea. One of the ways in which we'd stated it earlier was to say, feeling the normal reaction from the floor that keeps us at rest in the uniform gravitational field G on the Earth's surface is the same as feeling the contact force which would give that same acceleration G when out in free space. And that is certainly one sense in which gravitation and acceleration are somewhat intertwined. But there's another one, of course, which we talked about earlier. In Newtonian thinking, weight is thought of as the force of gravity on an object, and so real weightlessness would only occur in a spaceship which was far away from any other gravitational influences. Where the total force of gravity in that region was actually zero, it would then be truly weightless. However, we said that in Newtonian gravitation, a form of weightlessness can be experienced when freely falling in a uniform gravitational field. And that free fall could be whilst in orbit around a planet, or it could be when simply falling towards the planet within an enclosed spaceship or in a broken elevator. In these kind of situations, although we would describe things as weightless, there would actually be, in the Newtonian sense, a force of gravity on the object, and it would, strictly speaking, have Newtonian weight. So the equivalence principle seems to be implying not only that this is indistinguishable from this, you can't tell them apart. In other words, a constant acceleration out in free space is indistinguishable from a uniform gravitational field on the Earth, but it also seems to be saying that this is indistinguishable from this. You cannot tell these apart. That is, floating out in free space, away from any masses at all, is indistinguishable from falling freely in a uniform gravitational field of the Earth or any other uniform gravitational field. Having argued the case for the equivalence principle, we now want to emphasize the fudge that we had to include in order to make the case. We can't really say that gravity is the same as an acceleration, full stop. We've certainly argued the case that they are, but that's only because we slipped a word into the argument. One of the words that we kept on inserting into the discussion was the word uniform when talking about gravitational fields. We talked about a uniform gravitational field. Uniform or constant accelerations were said to be equivalent to uniform gravitational fields, and that's all well and good. However, there is strictly speaking no such thing as an extended uniform gravitational field. If we're talking about real gravitational fields like the one around the Earth, or any large mass for that matter, it has field lines which are directed towards the centre of the mass. They are converging. The field is, strictly speaking, non-uniform everywhere. If you could find a place where the gravitational field was perfectly uniform over an extended region of a particular frame of reference, which you couldn't by the way, but if you could, then the equivalence principle, as stated earlier on, would be true. In that case, we could take the uniform gravitational field and replace it with a constant acceleration. The whole frame of reference would be said to be accelerating, and we could then dispense with the gravitational field in our mechanics and calculations. To do this, we could use some sort of coordinate transformation. You would not be able to tell if it was a uniform gravitational field or a constant acceleration. The new frame with the constant acceleration would be indistinguishable, physics-wise, from the old frame with the supposed uniform gravitational field. However, as we discussed earlier, a gravitational field can never be perfectly uniform. Granted, if you zoom into a very small region of space where a gravitational field exists, then the field could be considered to be approximately uniform, and so this could be mimicked by a constant acceleration and vice versa. But in reality, gravitational fields from planets and stars and the like are never actually uniform, so that even in a very small region of the field you should be able to tell, in principle at least, whether you were accelerating or whether you were in a gravitational field. And it's vitally important that you accept and understand the reality of the equivalence principle, even with this caveat about uniformity. That said, I think for most people, when they think about it, the equivalence principle does seem like common sense. However, as to why it should be, takes a little more thought. And if you have thought about it, you may be beginning to realize that the equivalence principle is somehow related to the equivalence between inertial mass and gravitational mass. Why do I say that? Well, because it hinges on the idea that the accelerations of different masses in a given gravitational field are all the same. In our Newtonian formula, which equated the gravitational force of attraction between little m and big M to the effect on little m, namely mass times acceleration, we take these two masses to be the same so that we can cancel them, and then we say that the gravitational field strength on the Earth, ignoring the sign, is gm over r squared. In cancelling the two little m's, we are essentially saying that inertial and gravitational mass are the same as each other. Newton had realized or assumed this in his work on gravitation, but without understanding why they're the same thing, and the why relates in some ways to our thinking around the equivalence principle, the way in which accelerated movement of inertial mass is somehow equivalent to a gravitational force on the mass. Remember, Einstein wanted a theory that would show that the laws of physics must be capable of being written in such a way that they are the same in non-inertial frames of reference, when, for example, one of the frames was undergoing an acceleration. And that hints at the idea that the theory could well involve gravity, although it would clearly not be a simple case of replacing every acceleration by a gravitational field, because gravitational fields are never, strictly speaking, uniform. Einstein realized that he needed to find a mathematical way of describing the gravity-acceleration connection, and very importantly, he realized that any new theory would need to link gravity with geometry. But why geometry? Well, I suppose, to put it simplistically, if you had what seemed like it could have been a gravitational field, and if, by a change of reference frame, you could make it look everywhere like a constant acceleration with parallel lines, then it clearly could not have been due to a real gravitational field. Changing what seems to be converging lines into parallel lines is a geometrical issue, and it can be done for small regions of space. However, if gravity is involved, there's no way it can be done in one fell swoop for an extended region of space. You cannot apply a coordinate transformation to something like this and hope to make all of these converging lines parallel to one another. It's impossible. You might, of course, be able to use a coordinate transformation on a very limited region of this space, say here, such that the lines in that region were then transformed to being parallel. And in that case, that part of the space could perhaps be represented by a constant acceleration. However, that coordinate transformation, if applied to the whole space, would not do anything useful for the rest of the space. And I hope it's becoming clear that an extremely important part of Einstein's general theory of relativity, therefore, will relate to the idea of coordinate transformations, changing the shape and sizes of coordinate lines in a frame of reference into something more convenient. It's tantamount to having a very different set of measuring instruments. A very simple example of a coordinate transformation is when we change from a polar coordinate system to a Cartesian coordinate system. This is a simple example, and basic school mathematics could be used to convert the readings or measurements in one of these coordinate systems into readings in the other. The r and theta of the left-hand polar coordinate frame could easily be converted to the x and y, or x1 and x2, of the Cartesian frame on the right, and vice versa. They are simply two ways of measuring the same two-dimensional flat surface. It's basic geometry. However, when we come to think about gravitational fields, we will need to consider the likelihood of much more exotic coordinate systems, and also consider that the space that they are being used to measure, rather than being flat like the surface of this screen, might be in some way curved or distorted, perhaps by a gravitational field. We will begin that exploration in the next video, when we will start to consider some Riemannian geometry. However, before we do, it might be useful here to explore in a little more detail what we might call the Newtonian idea of gravitational field lines, and some of the physics and mathematics that's been developed around them. This will involve a much simplified discussion of Gauss's theorem, which, although it won't be needed for some time, will be helpful when we get deeper into general relativity. So here goes. We've shown that the acceleration due to gravity little g at some distance little r from the centre of mass capital M of an isolated object such as the Earth is given by minus gm over r squared, where capital G is the universal gravitational constant, and although this is not strictly a vector equation, the negative sign is there simply to remind us that the acceleration is in the opposite direction to the radius vector r. Gravity is an attractive force. This little g is also called the gravitational field strength, or simply the gravitational field. It is a vector and points towards the centre of the mass. The usual units for acceleration, meters per second squared, are identical to those of gravitational field strength, Newton per kilogram, which means that little g can also be thought of as the force that would act on a unit mass if it is placed at that point in a gravitational field. This gravitational field itself can be pictured as a set of field lines pointing towards the centre of mass of the object, much like the electric field lines around a negative charge. If we could assume a point mass, capital M, in a space, then we might picture the field lines like this, where the dot at the centre is meant to represent a point mass at the centre. Notice that the field lines produced by the mass M disappear at the mass. They don't come out again on the other side, and that's obvious, I suppose. The field lines are giving an indication of the direction of the gravitational field, and it is inwards. A more realistic situation, of course, would be if we had an extended mass m, such as the spherical shape depicted like this in 2 dimensions. In our earlier discussions, we tended to assume that the mass is homogeneous, so that it is spread out evenly throughout the whole volume. In other words, we can assume that the centre of mass is at the geometric centre. In that case, we would depict the field lines like this, heading towards the centre of the mass. Notice that we would not try to show the field lines inside the mass, and the reason for that should be obvious. From the very brief discussion that we had in video number 1, which touched upon Gauss's law, we realised that the field becomes weaker towards the centre of a sphere of homogeneous density like this, and eventually it becomes 0 at the centre. The gravitational field lines, if you like, disappear by the time you get to the centre, but how this happens is not easy to depict in a diagram. The field lines can certainly be considered to enter such a homogeneous sphere like this, but some of them can be thought of as ending on mass here, there and everywhere until there are no lines left at the centre, and of course that couldn't easily be drawn. In this short discussion then, we will initially focus on the lines outside of the mass, which have been produced by the mass and which are heading towards the centre of it. But how many lines should we draw? Well, I'm sure you know that the number of lines we can use to depict a situation like this is, strictly speaking, arbitrary. We could draw any number of them on a diagram if all we wanted to do was to depict the field. However, when thinking of the physics, it's helpful to suggest that the number of lines will be in some way dependent on the gravitational field value. You can draw what you like, but for certain formulae that we're going to derive, we will talk in terms of there being a particular number of lines for a given situation. And we will even think in terms of there being fractions of lines. The rule that we take is that when we have a gravitational field in some region, say, of value little g, then we will consider that the number of field lines passing through a unit area of that region, including fractions of lines, will be equal to the value of little g. This idea illustrates in a very simple way the fact that the gravitational field is weaker here, where there are fewer lines going through this red area, than here, where there are more. We may find, for example, that there are, say, 3.24 lines passing through each square metre here, and only 1.71 lines passing through each square metre here. That would simply be a way of saying that the gravitational field somewhere here is 3.24 metres per second squared, or newtons per kilogram, whereas somewhere here it is only 1.71 meters per second squared or newtons per kilogram. As mentioned in earlier videos, these gravitational field lines are analogous to the flux lines that are used in electrostatics. In fact, we can call them the lines of gravitational flux. If the field's little g was constant or uniform at a particular place with parallel, equidistant lines, and the plane of the area was at right angles to it, in other words, the area vector was parallel to g, then we could write that the total number of lines passing through the area, the flux, was simply the field value g times the area. And you will know that this g dot A is a scalar product or dot product, where we consider the area to be the vector perpendicular to the plane of its surface. The units of this gravitational flux come from the formula, must be meter cubed per second squared or Newton meter squared per kilogram or whatever else you can turn these into, but we will probably just refer to them simply as a number, the number of lines of gravitational flux. Obviously, if the field is not uniform, but rather different in different places, varying in both size, closeness of lines and direction, and perhaps if the area were at some different angle, then in order to find the flux through the area, we would need to do an integration of g over the area like this, where this double integral sign represents the integration over both of the two dimensions of the area A. So going back to our isolated and homogeneous mass capital M, it should be easy to find the total number of lines of flux that this mass, capital M, seems to be drawing into itself. In other words, the total flux for which it is responsible. This would be given by the integral of GdA if we take the whole area around the mass. This time we show the double integral sign with a circle in it, simply to indicate that the two-dimensional surface area integral is all the way around this spherical mass M, and it encloses it. So with an isolated mass capital M like this, which could, I suppose, be the Earth, we can choose any outside radius that we wish in order to perform this calculation for the total number of lines of flux, because the number of lines passing through this red sphere is the same as through this one. We could even use the actual surface of the spherical mass, like this, shown by this red line. Now the area of a sphere is 4 pi r squared, where r is the radius, and as we're considering the red sphere in this diagram, which is concentric to the spherical mass m, it means that its surface is always at right angles to the field lines, and so we don't actually need to do any integration. We can simply say that the flux for this mass capital M is the straightforward multiplication of the little g at a particular radius times the area of the sphere at that same radius. In other words, it is minus gm over r squared times 4 pi r squared, which gives minus 4 pi gm. In other words, the number of gravitational flux lines taken in, if I can use that phrase, by the mass capital M is simply 4 pi gm, the minus sign indicating that they are coming inwards. In doing this calculation, we have effectively used what is called the integral form of Gauss's law. This form of Gauss's law uses the field value g and the area of an enclosed shell around something to calculate the flux into or out of the mass. In this case, of course, on account of the symmetry and simplicity, it ended up being a simple multiplication rather than an integration. There is, however, another form of Gauss's law which you have probably come across, and this gives exactly the same answer for the flux. It is called the differential form of Gauss's law, and it's written like this. With this, instead of calculating the integral of the field across the surface around the mass, you look at the volume enclosed by that surface and integrate or sum the divergence of the field, shown here as div g, over that volume. The 3 integral signs indicate that the integral here is over the 3 dimensions of space for the volume enclosed by the shell. Gauss's theorem says that this expression should give exactly the same answer as the previous area integral. Now, if you need reminding or you've never done it, the divergence of the vector little g is a measurement at a single point in space. It measures the difference between the number of flux lines that come out of the point under consideration and the number that go into it. It's out minus in. In 3 dimensions, the divergence of the gravitational field strength at a point can be written as the addition of 3 numbers, 3 scalars, 3 differentials. The rate of change of the x components of g with respect to x, plus the rate of change of the y components of g with respect to y, plus the rate of change of the z component with respect to z. Or, of course, we could write it like this, with x1, x2 and x3 instead of x, y and z. You should recall that the div operation itself uses a kind of vector operator with x, y and z components, or x1, x2, x3 components. And the divergence operation can be thought of as the dot product of this differential vector operator with the gravitational field vector g, and it results in a scalar. If this divergence at the point is positive, then more lines come out of the point than go into it. If it's negative, then the opposite is true. If it is 0, then the sum total of what comes out of a point minus what goes in is 0. What comes out equals what goes in. This means that if we integrate this div g over the whole volume, which encloses a mass, the 3 dimensions, it will, in a sense, add up all those measurements of out minus in and give us the total difference between the number of flux lines that come out of the volume and the number that go in. That then is exactly the same as the flux in or out of the surface area enclosing the volume, and so it must equal the integral form of Gauss's law. Now you can look up the rigorous proof of all this if you've forgotten it or you've never done it, but the upshot is that with our isolated mass m, we can say that for surfaces which enclose the mass m, and hence the volume within that surface, these 2 expressions for the flux must both be equal to minus 4 pi gm. Okay, so that should make reasonable sense, even if you've forgotten most of your vector analysis. Now, before we finish this video and move on to some Riemannian geometry, I want to play around with some of this mathematics to get something that may seem fairly pointless at this stage, but will be extremely useful in the future. If we consider the mass of the object capital M to be homogeneous, we could surely say that it could be written as its density rho times its volume. Or rather, just in case the mass of the sphere is not homogeneous, we would say that the total mass is the integral of its density over its volume. And so if we take the equation that we've just found and substitute it into this new expression for the mass m, we get this. Or, rearranging, this. However, by inspection of this, it's clear that div g must be equal to minus 4 pi g rho. And that is an interesting relationship. Okay, granted, all we've done is a little mathematical manipulation, so this is no big deal in one sense. But the thing to realize is that this formula applies to a point in space. In other words, it is saying that at any point in space, the divergence of the gravitational field G at that point, which is the flux coming out of the point minus the flux going in, remember, only depends on the density of matter rho at that point, as well, of course, as on the constants minus 4 pi big G. To put it more simply, the number of gravitational field lines coming out of a point in space only really depends in Newtonian terms on the density of mass at that point. Now, this relationship will be useful later, much later, when we come to consider Einstein's field equations, the equations of general relativity. In fact, this 8 pi g here in Einstein's field equations is basically derived from this 4 pi g here, the extra factor of 2 coming from somewhere else. And I think you might be able to guess that the whole of the right-hand side of the field equations here has something to do with the gravitational effect of the mass density and the like which the space contains. I say and the like because this T will not simply be mass density, but will include energy density and other things, anything that can act gravitationally. Remember, mass is equivalent to energy. All of this will hopefully become clear later, much later. But for now, before we finish, let's just explore this a little bit more and maybe clarify a few things on the way. Still thinking in terms of Newtonian gravitation, consider again our isolated mass capital M. The only mass here is the mass m, and that means that the density of matter everywhere else, including at this point out here, at this yellow dot, must be 0. That in turn means that if rho, the density of matter at this point, is 0, then our Newtonian formula says that the mathematical divergence of little g at the point must also be 0. So we have this, or this. And when div g is 0, it means that whatever flux lines go into a point must also come out of it. There is 0 resultant. Let's think about that. Let's expand this little bit of space and consider the very small volume enclosed by this yellow dot. There being no mass in that volume, then the field lines that go into it must also come out. It will look something like this. Notice that I've illustrated the lines only slightly converging. This is because we're looking at such a small volume of space that the lines will in fact be practically parallel. But even though they are not really parallel, it should be obvious that what lines go into the small yellow volume must also come out of it. And that would be the case for whatever shape the yellow volume was. Consequently, even if we let the yellow volume shrink to 0, to a point, we can say that the out must balance the in at that point because there is no mass there. And that means that the mathematical divergence at that point must be 0. Div g at the point is 0. This is just as well as our formula says that if the mass density rho at a point is 0, then the divergence of the field at that point must also be zero. It's important to understand this because it might seem superficially that because the field lines are getting closer together, then we ought to say that there is less coming out than going in. And that's not what we're talking about here. It's not what the lines superficially look like, spreading out or coming together, diverging or converging. It's not that which matters in this formula. It's what goes in and comes out of a point. The point being a volume that has shrunk to zero size. It is that which determines the mathematical divergence div little g, and div little g at a point is always minus 4 pi big G rho. Okay, so hopefully that makes sense for this position, the yellow dot, where there's no mass present. What goes in must come out. However, let's now consider somewhere inside the spherical mass m, say somewhere around this yellow dot here. Clearly the density of matter in the small region of this yellow dot is not zero. It has a positive value, and so our divergence formula for a point around this yellow dot does not give zero. It actually has some negative value. Again, let's expand this portion of space and investigate this small yellow volume. It has mass, because it is a small part of the total mass, capital M, and we should be aware by now that gravitational field lines end on mass. This means that some of the lines going in to this small yellow volume will not come out. They will end on some of the mass in it. And don't forget, we can talk in terms of fractions of lines disappearing. The field will be weaker on the outgoing side of the yellow volume. And this is clearly impossible to draw, but here's an attempt to picture it. This picture is trying to illustrate that for some of the gravitational field lines, or even fractions of, the mass within the yellow volume will be their sink. And so what comes out on the other side will be less than what went in. The gravitational field will weaken as you move towards the centre of the mass capital M. If we then let the yellow volume approach zero, we can then say that the out is less than the in at that point, which in turn means that the mathematical divergence at the point div g must be negative. Once again, this is in agreement with the formula. The idea we're trying to emphasize here is this. When we have some finite value of the mass density at some point in space, then the mathematical divergence of the field div g at that point must be negative. Some lines of flux, or fractions of them, are absorbed at that point, and they are absorbed by the mass that can be considered to be there. Fewer come out of than go into the point. The lines of flux are decreasing, as is the field value little g. We could therefore even imagine an extended region of space where the density of matter, or energy even, within it was not constant, where it was not homogeneous, but rather had a density which varied in some continuous way. This picture is meant to represent a region of space such that the darker the shading, the greater the energy density, or, in Newtonian terms, the greater the mass density, rho. In a case like this, the pattern of the gravitational field lines would be extremely complex, and once again impossible to draw. Complicated as it might be, however, we can say that at any point in the space, div little g, the difference between the number of lines leaving the point minus the lines entering the point, must depend on the density of the matter at that point, according to this Newtonian formulae. Okay, we are now in a position to start thinking about some of the mathematics needed for general relativity. We've looked at Newtonian gravitation and we've seen some of its pitfalls, and we've also developed a number of equations from it which will be useful when thinking about Einstein's field equations and black holes and the like later on. In the next video we will start to consider some of the other groundwork needed in order to get to general relativity. For starters, we will look at some basic Riemannian geometry, and although the mathematics we'll be looking at won't be too difficult, there is so much of it that it can become really very confusing. And to cope with this, mathematicians have a new form of shorthand which will help just a little to make the equations look simpler. All that will begin to be discussed starting at a very basic level in the next video in this series, number 3. This video, number 2, focused on inertial and non-inertial frames and led to a discussion of the equivalence principle, and then considered coordinate transformations with a brief look at Gauss's theorem. In the next video, number 3, we'll move into more general relativity with an introduction to Riemannian geometry in 1, 2 and 3 dimensions. We'll also discuss covariant and contravariant vectors in 1 dimension and think about their transformation from one frame of reference to another.